Hello and welcome to the Physics 100 lecture series for Mount San Jacinto College. I am Professor Lee and I will be your instructor through this conceptual physics course. Well, I have assigned a textbook, Paul G. Hewitt's Conceptual Physics, and will be following the general structure of this book. These lectures are standalone and will be my primary method of instruction throughout the course. There are things that are going to be in the textbook that aren't in the lectures, and there are things in the lectures that aren't in the textbook. So if you want a more complete concept of physics, then I would recommend getting both and looking through and cross-referencing. But these lectures should be enough to get you through the course, and they should be enough to get you a good idea of what science is and what physics is. So starting out, we're going to go through chapter 1 about science, which goes over the scientific method and a brief overview of what physics is versus other sciences. What we would generally term science today used to be termed natural philosophy in Western Europe up until the scientific revolution in the 16th century. So people have been trying to explain the world for most of human history, if not all of human history, but science relies on the scientific method, which was popularized by Sir Francis Bacon in the 16th century. And that is what differentiates science from natural philosophy and other worldviews that were going around at the time. So, what is the scientific method? The scientific method does not have a clear definition, but in general, the most important aspects of it are written out in the textbook for scientific thinking. First, you have to recognize a question or a puzzle, such as an unexplained fact, then make an educated guess, which is called a hypothesis, the most important part of science, that might resolve the puzzle, predict the consequences of the hypothesis, perform experiments or make calculations to test the predictions, and formulate the simplest general rule that organizes the three main ingredients: hypothesis, predicted effects, and experimental findings. So this is called Occam's razor or parsimony, and is one of the most important ideals in science. So when we have gravity, we can make the prediction that all of gravity is caused by little gnomes, invisible and pulling down on everything in the universe at any given time, or we can use Newton's or Einstein's theory of gravitation, which are much more simpler and explain everything without having to make these assumptions. So Einstein, I think, said it best. Einstein is probably the most famous physicist in history, or at least in the past 150 years since Newton. And he said that every theory must be made as simple as possible and no simpler. So, what makes a hypothesis scientific? A hypothesis must make a prediction and be disprovable. So, astrology, which is the ideal that our destinies are controlled by the stars and the planets, is not scientific. But on the other hand, neither is string theory, which is a very popular theory in physics that all particles are made up of tiny little strings that does not make any predictions and cannot be disproved. So, by this argument, science is a rather recent development in human history, but there is a tendency among scientists and academics to use this as a form of cultural snobbery, veering on racism. While the scientific method is fairly recent, and most of the scientists that we are going to cover in this class are Western because of the development of the scientific method, cultures all over the world have been observing the universe. So, going back to this ideal, Einstein said, no number of experiments can prove me right, a single experiment can prove me wrong. And that is the very core of a scientific hypothesis. It has to be disprovable. A consequence of the ideal that scientific theories must be disprovable, and the ideal that scientific theories do actually tend to be disproved to a certain extent after a certain amount of time, is that we start with a theory or a hypothesis that does make predictions and is right to a certain extent, but that can be refined as more data comes in. So, an example of this is astronomy. So, since ancient times, we've been looking at the movement of the planets, and we've been able to predict the movement of the planets as they go about their orbits. But we had the idea that instead of orbiting the sun, these planets all orbited the Earth and had geocentric orbits. Geocentric means that it's centered on the Earth. So if you have a geocentric orbit, then you have these orbits like the ones that you see on the screen for these different planets. These do make predictions. You can tell where Mars is going to be at a certain given time in the sky based on these drawings, but they don't tell you a generalized form of the ideal or of the orbits. So from looking at the orbit of Uranus, you wouldn't be able to tell the orbit of Mercury. So this was a theory, and it's not as far-fetched or as backwards as it seems, but we eventually came up with the ideal, or Copernicus came up with the ideal, that instead of orbiting the Earth, the planets orbit the sun. And if the planets orbit the sun, then you get these much cleaner and much nicer orbits, which are either circles or ellipses, which are stretched out circles. So, like you would see for the comet in this drawing. So, what this means is that because they're all ellipses, because they're much more regular than what we were seeing earlier, we can probably make the assumption that any planet that we haven't seen before is also going to be following an elliptical orbit, which is something that Kepler built on and was able, one of Kepler's three laws, which we are going to go over, I assume, later in the textbook when we get to gravitation. But Kepler was able to make a prediction that any orbit is going to be an ellipse. And from this mathematical prediction, Newton was able to further refine it into a general theory of gravitation, which we are going to get into, as well as looking at these planets and looking at the circular or elliptical orbits, was able to formulate a lot of the ideas about mechanics that became Newton's three laws of mechanics. Mechanics is the motion of objects or the study of the motion of objects put into mathematical form. So astronomy is really the basis of physics, I think, especially in ancient times. So because these planets are so big and follow the same physical rules as smaller objects, we're able to make predictions about the laws that govern all of reality by looking at the planets and looking at the stars. This was more true in medieval Europe and Enlightenment Europe, but we still get a lot of information about uh, physics from planets. And the only caveat that I would make to that is in addition to really small or really large planets and stars, we now look at really small particles, which are just things like electrons or neutrons or protons or subatomic particles that make up uh, protons or neutrons that are going to also give us a ideal or an ideal of how everything in the universe works by looking at these very fundamental relationships. With this in mind, what differentiates physics from other sciences? So, my personal definition of physics is that it is anything that is too fundamental to be spun off into its own field. So, physics makes the assumption that the universe can be described by mathematical laws and doesn't really make any other assumptions other than what we are able to observe or what is the very baseline for the simplest process that we can find. So there is a subfield of physics called quantum mechanics, which, among other things, predicts that electrons in an atom have fixed orbitals. So chemistry uses the assumption of quantum mechanics in order to talk about the relationship between these orbitals and how they bond with each other and form chemicals. And then biology uses the assumption of chemistry to explain the biological processes, the chemical processes of living things. And then psychology applies this to the human brain. So we can say that sociology is applied psychology, psychology is applied biology, biology is applied chemistry, and chemistry is applied physics. But physics doesn't make any assumptions. So it doesn't make the assumptions that there's just going to be orbitals and these are the orbitals that you're looking at. It starts from the very beginning with math and makes as fundamental of ideals as you can get. If, as I say, all science is applied physics, what do physicists actually study? So, what we're going to study first is going to be mechanics, which is the very basis of physics, and it's the study of motion. So, if we shoot a cannonball into the air, using mechanics, we are going to be able to predict where it will land. We are also able to predict the motion of the stars and of the planets and how things change when you apply a force to them, how the motion of an object changes when you push it or pull it or rev your engine. Thermodynamics is going to be mechanics or the study of physics generally with large scale objects, which are called microscopic objects, macroscopic objects, just to be clear. So that is the study of the phases of matter, solid, liquid, gas, as well as other phases, and of how heat interacts with matter as you have these large amounts of atoms interacting and having properties that emerge from their interactions. Electricity and magnetism is the study of charged particles and of charged particles moving. So an electric field is caused by a charged particle such as an electron or a proton. and a magnetic field is caused by a charged particle moving at some speed. And it turns out that these laws that govern electricity and magnetism also govern light. So the next thing that we study is going to be atomic and nuclear physics, which is the study if thermodynamics is the study of macroscopic objects. Atomic and nuclear physics is the study of the smallest objects that we can find. So that is generally the study of subatomic particles and how they interact. And they're called fundamental particles like electrons or quarks, which you don't have to know what they are right now, but they interact at these small scales, and by understanding how they interact, we can understand how the universe as a whole, these fundamental laws governing the universe as a whole. Electricity and magnetism further gives rise to this concept that Einstein developed called relativity, which is that if you are moving very fast or are near a large gravitational field, such as near a black hole or a very large planet, then you are going to experience time and space in a different way than somebody who isn't moving very fast or isn't near a large gravitational pull. So if you watch the movie Interstellar, during the planet where they're near the black hole, they age about 10 minutes while everyone around them ages decades. There's also a good Doctor Who episode about this same concept. And then quantum mechanics is a consequence of thermodynamics, which basically states that there are only certain states or energy levels or other physical properties that are quantized or only allowed to be certain in certain energy levels in certain states. And this gives rise to chemistry, as I said, because chemistry makes the assumption that there are only certain orbitals in an atom, and that assumption comes from the quantization that comes from quantum mechanics. Before I end, I want to go over an experiment from 235 BCE or around then, which, while it didn't use the scientific method, is a good example of scientific thinking and proves my point that there was scientific thinking and there were people trying to understand the universe for as long as people have been people. So Eratosthenes was the librarian of the Great Library of Alexandria around 235 BCE. And using a simple experiment, he proved that the Earth, while as I think about this, he didn't actually prove that the Earth was round, but he did prove that it wasn't flat. And making the assumption that the Earth was round, he found that the circumference was about 250,000 stadia or 29,000 miles, while modern measurements give a circumference of about 25,000 miles. So what happened was that in his day-to-day life, Eratosthenes heard a rumor that there was a well in Siena that at a certain time of day on a certain day cast no shadow, meaning that the sun's beams were perfectly parallel to it. They were going straight into it. So if the earth wasn't flat, then that would mean that any pillar that came out of Alexandria some distance away at the same time would be at a different angle with respect to the sunbeams and would cast a shadow while there was no shadow cast in the well in Cien. So what Eratosthenes did was wait for that day to come and took a measurement of the shadow that it turned out was cast in Alexandria by a 8-meter pillar, found that it was about an eighth of the size of the pillar, which corresponded to an angle of 7.1 degrees using trigonometry, which is the study of triangles, and which meant that the angle between Cien and Alexandria was about 7.1 degrees. So this having a shadow automatically just proved that the Earth wasn't flat. And using the assumption that the Earth was a sphere, he was able to multiply this the distance between Alexandria and Cien by about 50 times, because that's about how many times 7.1 degrees fits into 360 degrees, or going all around the circle, and was able to find the circumference of the Earth to be about 250,000 stadia, or 29,000 miles. So this is scientific thinking. He recognized the question or puzzle, which is the Earth round? If so, was the circumference? Make a hypothesis. The Earth is round. As I said, it could have not been round. It just wasn't flat. And then predicted the consequences of the hypothesis. If the Earth is round, pillars sticking straight out the ground will be hit by the sun at different angles. Performed experiment, which was to measure the angle that the sun's rays make with respect to the well/pillar at Cien and Alexandria at the same time, a great distance apart, and formulated the simplest general rule, which was that the Earth is round. So this seems remarkable, but it is the type of thing that was going on all around the world and that we've been studying for millennia. It's just that we've made a good deal of progress recently, and we call that progress and that mathematical formulation of that progress physics. So this is also kind of, even though Eratosthenes was of Greek descent, it does kind of undo the Western bias that nobody was doing science up until the scientific revolution, and that Columbus was the one that discovered that the Earth was round in 1492, because these ancient people were also doing science, or a type of natural philosophy, or a type of theorizing. It's just that they didn't formulate it in the same way that we do. So when you look into the world, I want you to be able to look, by the time this class is over, I want you to be able to look at the world through a scientific lens and understand that it's not only our recent developments that are scientific, but it can be thought of as a general rule for all of humankind and for all human history. So with that said, I want to thank you for your time, and I hope that you continue the class and that you find it interesting, and that this class helps you to understand the world around you. If there's anything that I can do, it's just helping you to understand this. Again, thank you for the time, and goodbye.